8088. We're going to go more detail tonight about some of those, and then tomorrow, Thursday, we're actually going to go through all the processor types from historical to today. And so in some cases they went off and then disappeared. In some cases they went off, disappeared, and then went off again and disappeared. So we'll show you many examples of compatible processors. But the original one was an Intel 8088. What was the original software that went with the PC?
DOS. MS-DOS.
And it should be either one. I'll take MS-DOS or PC-DOS. Are you grading your neighbors? Are you grading your neighbors' papers?
Yeah, I used that before.
Okay, so your grade is grading. Okay. Number 3 may be difficult. Name A. There were 3 we talked about. 3.
Windows.
No. Read the question. Name a processor that Microsoft originally supported, but no longer. We named 3 last week.
Windows FB.
No, that's operating system, not processor. Okay, I thought this one might be a little tough.
PowerPC.
PowerPC is 1. So we have 3. We have MIPS, PowerPC, Alfred. Okay, so maybe that test is too difficult?
No, I didn't memorize it.
Okay, we're supposed to memorize it. I thought you would remember.
MIPS.
Alpha.
Those were the 3.
Alpha, MIPS, and PowerPC. No longer is Windows available for any of those platforms. I would accept for 50% credit if you said ARM. Because soon, I think Microsoft can support for ARM. Because it's not very popular. So if somebody said ARM, I would give half credit for that. Are you taking notes on your neighbor's quiz?
I'm writing the answers for him.
Oh, okay.
Yeah.
All right. What is the most important tool to take with you when you go to?
A clear mind. I understand.
Too close. I said
The brain.
The brain is #1 tool. What? Last Thursday, what did we do? Before we did anything, we looked, we read through the book, we tried to figure out. We never took any screws out. We never really needed a tool in this, so we used our brain first before we started taking things apart. We mentioned also, related to our brain, to use an egg carton to keep your screws, because I don't remember. So here's a nice little, you can put a piece of white tape in here, and mark which bin has what screws, and then you can set them aside, pull them back out when you're ready to put it back together. And then you can put another label in here and reuse it, so you can use this over and over. It's cheap, it doesn't cost you anything. This is how I can afford my tools. I buy and use cheap things. Okay. Bonus question. What is the answer to life, the universe, and everything?
Need money to spend.
No.
43.
Close. 42. I'll give you
42.
credit. Okay. So this was a Douglas Adams book. It's a
Oh,
bonus.
that's a stupid answer.
It's a bonus question.
Yeah, I know. That's a stupid story. I don't like that book.
Okay, so how did you guys do? Not so good? Okay, you can get back to your quizzes. You can get back to the drawings. How did you guys do? How well did you guys do?
The Douglas Adams movie used to explain it to him.
It's also a book. They were books, not movies. Books.
Power PC you accept, right? That's
Right, I
right.
see it, yes.
I got everything else right except for 43.
He's close, so we'll give you credit. He's got it. Okay, this is our number one student.
He missed one.
This is our number one student.
He missed two. First I put Intel. Do I get half credit for that? Intel?
I'll give you 1 4.
Fine. Okay, I'll take 2 fourths now. That's good. That's over at half. That's fine by me. She got 2 right. Yeah.
Okay. I promise next time that yours will be easier. But I do, now that you have good books that you can read, which with Texas and Teen, I expect you to review the material. I'm not going to have quiz every night, that's too much. And we'll have it on Monday, that way you can have the weekend to review the material. And probably maybe 2 or 3 weeks, you're going to start using this material with your own computers. So how many people in the class actually have a desktop computer? Or have access to one? You have access to one. Everybody's got one or has access, okay. So probably in 2 weeks, maybe 3, you're going to take your little book, you're going to open your computer, and I'm going to give you a sheet, and you're going to identify all the components that are in that computer, based on the material we give you. Second, at the very end of the class, if we have extra time, then we're going to have a workshop where you can bring your broken or dead machines into class, and as a group, fix
Well,
them.
I'd love to do that. I'd love to do that.
Jerry's case,
I've
you're
got
bringing
2.
yours next week. So bring one next week and save one to leave the class. You have 2 dead ones? You have dead?
I've got a lot of broken hard drives.
Can't fix drives.
Okay, shoot.
In the old days I could, but nowadays I can't.
Okay.
But we can test your drives and determine if they really are bad or not. I have a tester that we can plug in.
Okay. I have 2 questions from last week.
Okay?
The first one is, I need to know if it's off.
I know if the computer is off.
And,
It depends on the computer.
okay. And
I
memory.
always assume that it's on.
And there was some kind of problem that it didn't work, the IP wasn't working.
Oh, last night?
Yeah.
Wireless. Because they didn't renew my cell phone. My little box.
No. Last week, you used your computer, that small memory box, and you decided it wouldn't fit Windows XP. How'd you know it?
Oh, because it didn't have enough memory.
I've got to learn Windows OS size,
We're
right?
going to do that. We're going to go through that. Next week is memory. Next Monday is memory. So remember, memory.
Okay. And then second, one part was, I couldn't get out. What do? You can't get the part out. You just throw it, turn it off. What? How do you get it out?
You have to just carefully, sometimes, depends on the part. So sometimes the reason you can't get the part out is there's some hidden latch or screw that you can't see. We're going to open the computer up again tonight, if possible. If not, I'm going to show you some computers have 2 sides that open. So if you don't know the other side opens, then you don't know that there's a place to stick a screwdriver hand to take a screw out that's hidden behind. So I've had that problem on the drives that can't get the CD drive out because there's a screw on the back side. And you can only get access to that screwdriver by taking the other panel off.
It might be this video card. Some of those have a little button you have to push that.
So in the case of the video card, sometimes there's a latch that's you have to pop to where you pull it out because it'll be linked together and you can't pull it up. This is why you always look first and take a survey of how the system is put together. There's a very important order in which you have to put things in, or you'll get to some place and you can't put the next one in because that one was supposed to be first or somewhere earlier in the assembly. So much like you're identifying the screws, if you're pulling chassis pieces out, because you're pulling out boxes or whatever, remember the order that you pull them out. Most of the time the motherboard is the last thing to come out, which means it has to be the first thing to go back in. If you put the power supply back in, you may not be able to get the motherboard. It may not fit because it needs clearance to get in. So remember the order you took them out and reverse the order to put them back in.
Sometimes you take a picture of the case.
I sometimes take a picture. I did this last week. Where's my phone? I take a picture mainly to tell the owner what they were doing wrong or what you had to fix. If you go and let me give you an example. If they bring you a machine and it smells like it's burnt, like something burnt, then once you get the cover open, you may want to look inside and take pictures in case something did burn up. Otherwise, the customer might say, you burned up my machine. It was working fine until you touched it, and now it's broken, so you pay for my computer. So it's a good idea sometimes to take pictures. Actually, I do have. I just moved all my photos on my phone because I ran out of space. Maybe I still have it. When I was working on my old neighbor's computer, first symptoms was the computer comes on, power's on, and then immediately powers off. So I did the same thing. I looked inside around to see if there was anything wrong with the machine.
Same problem with mine. I think the fans are out.
Yeah, if the processor overheats, so there's a sensor on the processor, the temperature goes up high, it'll immediately turn itself off. So the fan is not working to cool it, it's got a protection mechanism to shut itself down. It's not working. I don't seem to be able to. I'll look at it on the right here. Okay. Any other questions from last week? No. So when you have a chance, you now have it. Now it's large enough for you to be able to read. You may want to look at this document online. We looked at it in class. I printed out a copy. It says, when I found it on the internet, it said it was for a compact, but really it was for an Intel motherboard clone. Build your own computer motherboard. Which you probably should just download one and just look it over and get used to the format so you understand where to look at the document when you're trying to find something related to the computer stuff. There's an example in there, and it's basically very similar to the motherboard that was in the computer we looked at last week. Very similar. Are there any other questions from last week? Tonight I want to give an overview of motherboards. It says motherboards, chipsets, and buses when I put the outline together. But then I realized I can't talk about the chipset without talking about the CPU. That they really have to go side to side. So as we go through the CPUs, we'll talk about the chips that go with it. Certain CPUs will have certain other components that are mandatory to go with those chips. So it's not only in this chapter, it will be in Thursday's class. We'll take it off the outline and change the outline. As I started changing the material, I realized that at the beginning of every chapter, we're going to have a section of terminology. And at the end of every chapter, even though we're not going to do it in this class, for your knowledge, there will be a quiz, mainly as a self-learning that you can look at home to see if you've absorbed that chapter's worth of information. So it's not, I'm not going to have it, you're not going to take it in the class every time. It's like a refresher quiz just to make sure that you've learned the information from this chapter. If this was a more formal certification, life and death type class, and I would make you take it every chapter. I make you take this. This is more relaxed. We're going to be doing a lot of things here that we're going to be doing together. This is not a teacher-student, separation type class. We're a group trying to solve problems here, so I'm a little more relaxed. So let's start out with new terms that we have for this section, and you might be used to these terms, or you may not. First term you probably heard, hertz. I'm not talking about hertz like hertz, not that hertz. Hertz as in wavelength, or as in cycles per second. Anybody radio? Anybody? Yeah. The radio is always, your frequency on your radio is in some hertz. Television technically is in hertz too, but they just say channel. Nobody specifies a TV channel by its frequency, its hertz. For this class, we're going to use it as a measurement of clock rate, how fast the clock is ticking off, or how fast we're transferring information. It's basically referred to as cycles per second. How many times am I going to do something per second? And you take the hertz, and you take your, remember we said how wide a bus was? 8-bit, 16-bit, 32-bit. You take the hertz, and you take the width of the bus, and you multiply them together, and you get usually the transfer rate. So I took the original IBM clock rate, which was 4.77 megahertz. And I took the fact that it was 8 bits wide. I'm going to get about 32 to 40 megabits per second. That's the maximum. But that's a theoretical limit you never really truly get to. This is like the MPG for your automobile. This is what the government says you should get, but in reality, you're going to get some number less than that. And the reason is that even though this is the speed the lane is, much like the freeway, you have to leave gaps in between the sections of data. So you actually can't transmit data at max speed. But the highway is rated, in this particular case, the highway is rated for 40 megabits per second. Traffic throughput might be 30 megabits per second, or less. We're going to use the term bus many different times. A bus is just a logical concept of a place for information to be exchanged from one place to another. Now, it may be a physical, or it may be logical. It may not physically exist. It might be virtual, but in most of the stuff for this class, they are going to be physical buses. So we're going to talk about tomorrow, on Thursday, we're going to talk about the memory bus. The memory bus is a pathway for data to move from main memory to the CPU and back. And there are other buses on the system as well.
Not through cable?
Not through a cable. It's actually in the motherboard. The cable, in essence, is a bus. So you can think of the cable being a bus too. But some of the stuff on the motherboard is actually on the motherboard. Memory doesn't go through a cable. Memory actually goes through the back. And I'll show you when we go through some examples. We'll look on the back of the motherboard. You can actually see the wires running in parallel that actually forms the memory bus. Okay. I'm not going to go into a lot of detail tonight about memory buses, because we're going to do that when we talk about memory on Monday, next Monday. I don't want to cover it twice. When we talk about like the drives and some of the other, every time we're going to go through that, we're going to talk about the different buses and how the information is sent. In this class also, except for one exception, all the buses are in parallel. Meaning each wire is going to carry one bit of information at a time. There's one example at the very end of tonight's class where it's a serial bus, meaning the bits, there's only one bit and everything's traveling one after another. You'll hear the term, everybody got that? You'll hear the term PCB, or you probably not hear it, you read it. Printed circuit board, yeah. Not the stuff that gives you cancer. Not polychlorobenzene. I don't know how you say that.
Right.
But usually they'll say the PCB, meaning the motherboard or the video card. Insert the PCB into the slot. They'll use the shorthand instead of saying. Hold on.
If it's at all possible to turn down the brightness of the projector just a little bit, if it's too much trouble, don't worry about it, but it would be very cool.
No, right.
Okay.
next one is card edge. It usually means it's a type of connector. So what a card edge is where you look at the PCB, you'll see metal signals on the back of the PCB, and then you'll see metal directly on the edge of the card.
It's not the slot.
No, it's actually the slot might be card edge, but generally it goes to the board. The board has a card edge connector.
Like on the video card.
On very old video cards. I'll show you an example later on. And when we talk about other types of motherboards, I will talk about, most of the time they talk to it as a slot. They refer to it as a slot. And sometimes in some of the older literature, they'll refer to it as a card edge connector. They're saying the type of connector, not the connector itself. The last two are just an introduction. We're actually going to go in great detail and these two different things late in the class, because you need to know how all the hardware works. Then we'll layer on the software and say how the software works. I want to introduce the term now in case it shows up somewhere between now and the time we get to that section. But as soon as you turn your computer on, there's a piece of software that always runs. It's called the BIOS. It stands for Basic Input-Output System. You can't change it without special tools. You can't erase it. It's supposed to be there so it guarantees that I can always turn on the computer and look at the hardware in a sense.
Question. If I update,
That's why I said generally. You can change it with special software. So you can change it with special software, but most people can't change it. In the very old computers, you couldn't change it. It was, you got it, that was it. I would say only within the last maybe 5 years are you now able to update the actual BIOS. In the old days, you had to take the chip out and stick a new chip in to get a new BIOS. And we'll show you on the motherboard. We'll go back and look at that. That motherboard may have had the BIOS as a chip.
yes, question. It's not the same as a register?
No. Register is a Windows thing, BIOS is a hardware thing.
Okay.
And then part of the BIOS itself is a thing called POST. POST is power on self-test. It's most likely any message that you see coming on the screen is coming out of POST. I'm checking the memory, I'm checking the video card, I'm checking the hard drive, I'm checking other components of the system. These are power on tests. These are not full diagnostics. As technicians, we might want to run additional software. But this is just simple tests that the CPU will run to make sure it can talk to the other components before it tries to load an operating system. You don't want to go, I'll say this correctly. You don't want to start up an operating system only to find out you have bad memory. Because if the memory's bad, the operating system may still run, but it might do something that you didn't want it to do, or that the designers didn't want it to do.
Is it a safe mode, or will there be a safe mode?
Safe mode's a Windows thing. We talk about safe mode too. That's not POST. When we get to talking about the Windows operating system and how it works, we'll talk about safe mode. Safe mode's a very good diagnostic, but it's not the POST that we're talking about here. POST occurs before even Windows starts to power on. If you see a Windows logo, you're beyond POST. Another question?
So when we start the post, the BIOS, and then post, and we never see post really, or?
You may or you may not. So we'll show that when we get there. Sometimes you can turn off the messages.
So the BIOS is first. And then
BIOS, POST is part of the BIOS, so don't think of it as two separate things. Within the BIOS is POST. So BIOS contains the POST, the power on, and usually a menu system for setting, making changes to the settings. So there's many things inside the BIOS, part of it is cost. Okay?
Okay.
So let's talk about the different types of motherboards and the different sizes of motherboards, because you will run across, and someday you'll open a machine and go, this one's too small, this isn't the one I'm using. We already talked originally about the first two, the PCXT and the PCAT. You saw pictures of them in the original slides we showed when we were talking about the history. They have special formats. The XT format has long dead. That physical format is gone. It's not been used for 20, 30 years. The AT format lived on even after IBM stopped making AT computers, because it defined a certain format, defined where the screw holes were, it defined how the back panel looked. So people building systems or chassis always knew the components were going to line up. It's not good for one chassis manufacturer to put the hole in one location and the motherboard to put the hole in the other location, and then when you're trying to put the mouse or the keyboard, they're not being able to line it up because the holes didn't line up. The other thing that the AT format standardized on was how the power supply was designed and how the cables go into the motherboard. Again, we're not going to talk about power supplies now because we have a separate section on power supplies. But when somebody talks about, when you go to the store and you want to buy a power supply, one of the first things they're going to ask you, do you want an AT power supply or an ATX power supply? And they're not the same. Same if you were going to buy a keyboard. Most of the time now, you're not going to find an AT keyboard. The AT keyboard was a very large connector, as you saw on the diagram from last week. It was a big fat connector. ATX keyboards, also referred to as PS2 keyboards, are very small. Now, there was a time period where they transitioned, where when you bought an AT keyboard, they would give you an adapter to go to PS2 keyboard. Or if you bought a PS2 keyboard, there'd be an adapter to go the other way. There was also a time period with mice. The original mice were serial mice. We'll get to mice later, we'll talk about it. But now there are PS2 mice, and now you have USB mice. So remember in my kit, I had that little adapter. That's to get around the fact that the formats have changed over the years. If your microprocessor is a Pentium class or greater, and we'll talk about processors next class on Thursday, you probably don't have a PCAT keyboard. It'll be immediately obvious if you look at the back of the chassis and if you see a very large hole for the keyboard, it's an AT keyboard. It's an AT motherboard. What the ATX format did, the ATX format said, we want to get out away from IBM and their design. We want to change a few things. We want to change the way the power supply connects to the motherboard. We want to have some options for how the chassis is put together. We don't always want to have the keyboard in a certain hole position on the back of the chassis. So they wanted flexibility in the building system. So they defined a new standard for motherboards. And there are many, many different formats. I'm just showing three, and on the next slide I'm going to show you a couple different examples. The biggest one that you'll find will probably either be the ATX format or the micro ATX format. So here's where we're going to have a little show and tell. This is an old surplus. This is an ATX format. If you wait till we open back up the computer, you'll find this is exactly the same format that's in there. This is just a different organization, different components on it. We're going to use this for reference in the class when we talk about other things as well, but here's just a physical example. So there's many connectors on the back here. Now what ATX decided to do was to define a square that all the connectors had to fit in. And when you bought your motherboard, not only did you get your motherboard, but you got this little metal square panel that went around all the holes. It was the responsibility of the motherboard manufacturer to provide that panel, not the cabinet, or not the case manufacturer. The case manufacturer just left a square opening. They might give you a sample back panel, but it probably didn't match your motherboard, right? Only once have I ever been able to put two together and go, ah, it worked. You don't usually do it. Now, this is ATX. This format,
I still see the ATX around.
yeah, let's go see this. This is usually used for very large tower computers, where it's cheaper to make large ones using the ATX form factor than it is to make, say, a micro ATX, because they have to shrink all the components. I have to put all the same components on here on a smaller board. But the micro ATX format, let me get the orientation right, is designed such that, for the most part, it's physically compatible with ATX. So, if you look at the left portion, they line up. The connector squares in the same place. You'll see that the screw holes line up. It's just shorter. The board's not as wide as the ATX. And if you count, we haven't talked about the slots, but if you count the number of slots, you usually will have fewer slots on a micro ATX card because it's shorter. It's designed also. Or I want to make a thin desktop computer. I can make them smaller by using this form factor. You will probably see a lot of these.
Not for laptops.
We're not doing laptops, and we're not going to be doing tablets in this class. Those are custom made. And they don't have any, there's no standard for every laptop motherboard. Every laptop design has a different, because you have to fit it around the ergonomics of the design of the laptop itself. You can't fix a laptop by going to Fry's and getting a laptop motherboard. It doesn't work.
Interesting. Wow.
Alright, the last example I want to show is a micro ITX form factor. Micro ITX are used for very small, maybe a media center computer, or sometimes they're used in wide computers where they want the extra space for having drives, multiple drives. So you might see some servers that use a very small form factor like that to leave space. In this particular example, there's only one slot. And what generally happens is that you end up with a short but a fat cabinet, and this connector comes out and makes an L, and then your I/O cards are actually sitting like this. So instead of them sitting this way, they're sitting in parallel. So this is yet another form factor with a more dense connection. And every time you shrink it down smaller and smaller, you start to have more limitations on what you can put. But the square back panel is exactly the same. And if your case manufacturer is correct, you should be able to put this even in a chassis where an AT motherboard was, because it defines the standard. Let me give you an example. There's some pictures of some motherboards there of the various form factors. But if you were going to read the standard for designing motherboards, they fit into a very defined metric classification for each of the designs of the motherboards. And they assume that this 50 by about 90 is about as small as you can make without getting to really difficult. Most of the time, that very small form factor that they call PC-104 is only used in scientific instruments. And you're paid a lot of money for that form factor. As far as the kind of...
I'm wondering if they're gonna, what will be the next city to do smaller than that?
The one I'm currently working on, which is going to be the size of the drive. There are a couple other ones. You'll see the term EPIC here. This document is a little old, so they show you mini ITX, Flex AT, Micro AT. There's a B, there's a BX, BTX, and there's some Nano. There's a thing called Pico ITX. Pico ITX is only made by one manufacturer. Pico ATX is a standard that technically would go on the back of a hard drive. So if you wanted to make a portable computer that was the size of the hard drive, then you could make them together. But you're not going to have 15 connectors. There's just not going to be space for all the connectors. So you're going to be one video connector, one USB connector, no slots. You'll be very limited to what you can put on that. So general purpose computers are going to use larger size motherboards. Very specific control type computers might use the smaller ones. And so here, much like we just looked at here, show you some relatively size differences of the motherboards. This is the one I was talking about. This one was about the size of a hard drive, Pico ITX. Okay. Any questions about the physical form factor? If you were to overlay these three, the hole patterns that show up on this one also show up there. So the screw holes will go down. Now for the ATX, you're going to want to put extra screws in. As you can tell, this scrap motherboard that I've had, you can see that it's warped because it wasn't properly fastened down and the temperature caused it to warp up. This was not mine, by the way. I did not do this. I pulled this out of the scrap pile to bring it into class. I would never do that to mine.
I have a question. I think some companies like ASUS, at one time made some oddball motherboard cabinet combinations that didn't really comply to any spec, I think. Isn't that true?
Okay, so he was saying that there are some odd size. You may get to the case where it might look like an AT motherboard, but then the way the connectors go in or whatever, it turns out that it's designed only for that computer. Let me give you a key example. In the server market, where they put the servers into a rack cabinet, there's a definition of a rack unit which is 1.78 inches tall. It's actually shorter than that square that's used as part of the ATX form factor. Therefore, no one-use server is ATX compatible or certified. The way they get around it is they will go and take a manufacturer of their choice. They will go and say, I'm going to use this motherboard, and only this motherboard, or the motherboard that has the same hole patterns. Instead of putting a square bracket, they will actually cut out in the sheet metal openings for every connector. And as long as you have another motherboard that has the same physical connector positions, then you can replace it. But if you look at, on a break, if you come up and look, none of these really have the same hole patterns. Sometimes you might get away with it, sometimes you might say, well, I really didn't need these two USB ports. I've got these over here, so as long as I can have access to these, okay, fine. I'm okay. But if it blocks a video port, or that blocks the keyboard port or some other thing, it's going to be bad news for your customer if you try to wedge in an unsupported motherboard. So these are the standard form factors, and yes, just like the laptops, there are manufacturers out there that make their own form factor. I'll bring in, on Thursday, I'll bring in one of our little thin client computers that Weiss we make. And at first glance, you'll say, hey, that's an ITX form factor. But then if you get your ruler out, remember you're carrying your ruler with you. If you get your ruler out and you measure your hole patterns, you're going to find out I can't really put an ITX motherboard back into the hole pattern because it's not exactly ITX. It was never intended to be ITX, it just happens to look like ITX. Okay? So these are for standards, not necessarily all manufacturers. Okay? Now, there was a question or a comment earlier about buses. Are buses wires, or are they on the motherboard? Now, in this particular example, this is purely an example. This is an example from probably a fairly modern, maybe a 5-year-old computer. There are 1, 2, 3, 4, 5, 6, 7 buses in this computer system, not including any ones that are on a cable. And each one of these buses is separated out so that it can run independently and at the same time as another bus. In early IBM PCs, if you want to access the video card at the same time you were accessing the floppy drive, at the same time you were operating the hard drive, at the same time you were trying to print, all of those things had to wait. I'd give a little time slice to the video card, and I give a little time to the CPU, a little time to memory, a little time. In order to make faster computers, I need to be able to split that out and let the subsystems run individually. So for example, if I want to access memory, it's a separate memory bus. Now, some operations don't need to go to the CPU to access memory. Again, we're going to go into details tomorrow on Thursday about how memory bus works. But in some cases, the pathway may come from down here directly to the memory. And the CPU might go directly out to the video. And those two paths are individual, separated, not linked together. They can operate at the same time. And one doesn't have to wait for the other. In order to support expansion cards, you have to have a bus and you have to have some kind of slot technology. So in general, there will be a separate bus that drives the slots. And most of these buses run in parallel. So if I put 5 cards on that bus, most likely only one card can actually transmit data at the same time. So each card actually has to request, I need to use the bus. It has to make a request to have access to the bus. And it transmits the data, and then it releases the bus. There will be some future cases, again we're going to go into details, there'll be in some cases where multiple accesses to the bus can occur at the same time. One of the problems that the IBM PC and AT had was that when people filled all the slots with cards, the system grinded to a halt because each card was trying to grab the bus. And so a lot of software went into changing the request mechanism and the access method for complex systems that have multiple cards. Because the original thinkers didn't understand the implications of what occurred on the buses. I'm going to cover this bus, the memory bus, when we talk about memory. I will talk about this. These were examples of chipsets. So on Thursday, we're going to talk, what do we mean by North Bridge and South Bridge? We're going to talk about the graphics bus when we talk about video cards. We're going to talk a little bit about tonight just the format of it and how the video bus works. We're going to wait until we get to the video section. We're not going to go specific on things that you can put in the PCI slots, but we're going to talk about PCI slots in the next hour. And then when we get to I/O, we're going to go through all these I/O types and talk about the different kinds of cables that you need and how those I/O buses work. So in essence, each one of these is also a bus. The serial bus, the parallel bus, the floppy bus, the hard drive, these are also buses. In concept, they're just not called them by convention. But in concept, they are, in essence, buses also. I'm going to break right here, since we are on that first hour of class. Give you 5 minutes to go use the washroom. Give Ken a chance to swap tapes. Give me a chance to drink some water. Take my doggy out. Okay. 5 minutes.
He won't hear you, he'll have to.
Wi-Fi.
Oh, he wants it for here.
Oh.
No, yeah, because we want to use this.
I think he's trying to figure out the password for.
You're going to put this in your computer and then you access.
But he should be paying attention to class and not searching the net.
Yes, most,
No.
I don't need it. I need it. If I need it, no, I need it, I just put this. Try to pay me to do this.
No, the company pays for that anyway, right?
That's right.
Yeah.
Okay. Any questions? Did everybody follow that the first hour, or is that okay? Right speed?
No, I'm just trying to get he's locked up with the Wi-Fi or something.
No, the Wi-Fi, I never got the Wi-Fi to work there.
You have not?
I have not. Local. No, if you need to have access, I can bring a box. I was telling Jerry that we have a box that will connect to here. If this module plugs into it, that takes cell phone and converts it into Wi-Fi. So far, we've not needed internet here, so I have not turned it on and hooked it up. So if we need to, then I can turn it on. Technically, I can turn this laptop into Wi-Fi if you really need to have it. All right. Everybody good?
No, that's just not working. Wi-Fi is not working.
Because you're supposed to pay attention to me, not Wi-Fi. Okay? Same with these two.
We're talking about lows. You gonna start the class now?
Yes. In 5 minutes. Actually, then 10 minutes.
We need your attention.
Yes, we might need to pay attention. Okay. We're going to talk now for the rest of tonight strictly about the I/O card slot buses. Because this will take a full hour to go through the different formats. We're not going to go into deep understanding, but we're going to give you an overview of the different kinds. Later on, we're going to go more into detail about the modern ones. This is just an historical background, just in case you see a slot and you need to know what to do about it. So the original The original bus that was used by IBM has been renamed to ISA, which stands for Industrial Standard Architecture. It was used on the XT, it was used on the AT. After that, Microsoft deviated. They went off and they did their own proprietary format to block the clone manufacturers. They did an architecture called the MCA. We're not even going to cover it here, because MCA went off the cliff and died. But the AT bus continued on, so even after IBM came back and started making machines post-MCA, they went back and started using ISA bus again. So the ISA bus existed, and it didn't exist at IBM, it existed at other companies, and then it re-existed in IBM.
I thought IBM sold their hardware things to.
We're talking old days. We're not talking in the last one. Yes, IBM has sold their PC and laptop business to Lenovo. It still has a server business, but they don't make printers, they don't make laptops, they don't make desktops. All right. So this is the picture of the card. You have it in your manual. And this is the format. I just wanted to give you an example of the format, because we're going to see that this very similar pattern is going to exist, where there'll be a mandatory connector, and next to it will be an optional connector. So in the ISA standard, the mandatory connector was the connector that provided the 8-bit bus. This was backward compatible all the way to the XT. So if you had a card in the original XT that you designed or did a special function, up until maybe 2 or 3 years ago, you could still use that card in any computer, because they kept that standard and brought it forward. But they added to that standard as they went along. So when the AT was designed, the AT designed to make it a 16-bit bus. And the way they got the 16-bit bus is they added the other 8 bits into a second connector, into a parallel connector. So all the address information, all the signaling information was in the first connector. The second connector just added extra lanes on the highway. We had 8 lanes here, and then we had 8 lanes, we made 16. A few manufacturers went beyond that and said, I need even more space. So they designed a third connector and extended it out to be 32 bits. But you need to have a 32-bit capable computer chip to take advantage of that. The XT was only 8-bit, the AT was 16-bit, so it stopped right there at 16-bit. The rate at which it transfers information started out at 4.77 megahertz. Remember the first night in the class I said this computer here was 1,000 times faster than that original. Because this is in megahertz, this is in gigahertz, this is 8-bit wide, this is 32-bit wide. So it's most likely not 1,000 times faster, it's most likely 4,000 times faster. Because the highway is 4 times as wide, and the speed of the highway is 1,000 times faster. When IBM made the AT, they increased the clock rate to 6 megahertz. And then in some special cases, for other clone manufacturers, They increased it even more to 8 megahertz and 10 megahertz. This became a problem on some cases because if I had a car that only operated at 4 megahertz and I stuck in a system where the bus operated at 10 megahertz, it may or may not work because I might be driving the car too fast. Just because the freeway is rated at 65 miles an hour doesn't mean that every automobile ever manufactured can go that fast. If you go take a Model A that was manufactured in 1909 and you try to push it 65 miles an hour, what's going to happen? It's either going to overheat or it's going to blow up. Same thing's going to happen with a computer. Exactly the same thing. It might start to work, but then the temperature might start to rise. And because the temperature is rising, the components might actually explode. And the computer may actually catch on fire. And this was a great concern by manufacturers when they were trying to support different cards from different companies that were designed for lower speed and putting them in the higher speed bus. This is one of the reasons that Apple closed its architecture. It's one of the reasons why IBM decided to go off and make MCA. Because if they controlled the standard and they were the only one that could make cards, they could guarantee compatibility. It made it simpler to test, and it made the warranty better, because you were guaranteed that the cards work. This was okay for the 1980s. This rapidly became too slow. So the designers said, we need to have a faster bus. The first attempt at a faster bus was to supplement the ISA with another connector and then call the overall system Visa Local Bus. So Visa Local Bus had an ISA connector, and then it had the extended VL bus, or VLB, at the end of it. This brought the system up to 32 bits wide, but the way this bus architecture was designed, it was specifically designed to operate with the Intel 80486 processor, 486 processor. It meant that 386 computers couldn't take advantage of this. It also meant that when Pentiums came out, this bus basically died. Because it went hand in hand with the 486. So this was great for making the 486 bus fast, but after the 486 became old, then this bus disappeared. If you had a PC with it, you would probably have 1, maybe 2 VLB slots. And that was it. One for a video card, and one for the drive control. And that was it. There were very few cards that supported this bus.
So when did we start working on, you were going to tell me that, the Visa card?
Watch, we're going to go through it. Watch, see? Jump
Yeah,
ahead.
memorize that.
Jumped over the fence.
Okay. Sorry.
Around the same time that IBM took that MCA path, the rest of the international community said we have to have our own standard. If IBM's going to go off over here and do their own thing, we want to be able to say that our components are compatible. So they made the ESA bus, which stood for Extended ISA. And the ESA bus used a different kind of connector. It worked for 5 years, it was available, but it didn't really change the speed of the cards, it just made the cards lighter. Because they knew there were going to be compatibility issues trying to make faster cards. So this worked just fine until the processors started to outrun the bus. In those days, you would also find these really strange looking cards. Here's an example of one. This is a video card. When it's in this format, it's designed to go into an ISO slot. If you took the bracket off and moved the bracket here, and flipped the card over, you could put it into an ISO slot. So you start to see these really strange combinations and start confusing people, and people just stop. So this, enough is enough. We're tired of this. So in 1993, the PCI bus standard was submitted and surpassed the ISO because it was a cleaner, more defined standard. Which then leads us to the PCI bus. In fact, the PCI bus technically still exists today. So on some computers, you will actually have it. So we look at an example. So all these examples here actually have PCI bus on. Of all these motherboards, this is probably the most modern one. This is probably a 2-year-old motherboard. This actually had one PCI slot and some PCI Express. We'll get to the PCI Express and a couple more slots. So we kept this slot around because there was a very large investment in cards designed for the PCI bus, and we haven't significantly changed the way the bus works. So the industry decided we wanted to allow those cards to continue to operate in modern systems.
Will it end one day, you think?
No, we'll talk about that. Hold that thought.
That was
This is not hold that. Hold it. When the standard came out for PCI, they were trying to look back at time and look at the standards and try to learn all the mistakes the previous designs made. So they wanted to say we wanted to have different speeds of operation. We wanted to have the option for different data lists. We wanted to have the option for different power levels. So they built this all into the standard, and while the connectors all look very similar, there are slight differences in the connector and the slot to ensure that you didn't plug the wrong kind of connector into the slot. So if you look very carefully here, here's an example of a 3.3 volt slot, and there's a notch here. And if I had a 5 volt card, the notch is there. This was just to prevent you from putting the wrong version of the power card into the wrong slot. The rest of the signaling was exactly the same. So on every other pin, it was exactly the defined signal, and all they were doing is notching out the different power levels to allow you to have it. You could technically have a universal card where both notches existed, in which case I would look for either power and use whichever one was present. And just as I mentioned about having a mandatory connector and an optional connector, the same thing exists with the PCI bus. So for 32 bits, you just have this connector. And to get to 64 bits, they added this little part on the right. So again, just like the ISO bus, the first connector defined the address, the control lines, and the first 32 bits. The second connector just identified the remaining 32 bits of the data bus. So it just basically added 32 more lanes by adding an extra connector. You could technically put a 32-bit card in a 64-bit slot and everything's fine. There's no reason why you have to drive on all 4 lanes of the highway. In fact, if you try to drive on all 4 lanes of the highway, you're probably going to be arrested for drunk driving. So you could put different formats, and they made the connections to it. This PCI bus was invented in the 1990s. It's 23 years old this year. and it's still fairly going strong. It operated at 32 megahertz and 63 megahertz. Still not that fast, but when you look at it compared to the ISOBus, it's light years faster. About the same time that the PCI bus was being invented, a separate group was trying to figure out a mechanism to increase the performance for video. Because now I want to be able to do 2D graphics, 3D graphics, solid model, and the ISOBus was just too slow for transmitting video signals to the system. So they came out with the AGB bus, accelerated graphics port. It was a unique bus specific just for graphics. And your motherboards usually only had one of these on board. One of the computers we'll be bringing in later in the class, my old Sony, has an AGB slot. We'll see that works. If you need to have more than one video card, you had to put one in an AGB port, and you had to stick a second one in a PCI slot. And then you ran into the case that these two boards were not exactly the same, and so it required a lot of software control to make them operate because they were two different bus standards. It started out at 33 megahertz. It was expanded to 66 megahertz to get faster speed. And then they started doing this multiplexing scheme where they could send 2 times the amount of data per cycle and 4 times the amount of data and 8 times. So they're able to shrink. Even though the clock rate was still 66 megahertz, they were able to do 8 transfers for each clock cycle to get faster transmission. So in order to figure out how fast that video bus is, we would have to take 66 times 32 times 8. And that would give us the megabits or gigabits per second that could go through that bus. You will also see some other extensions called AGB Pro, AGB 64. This bus, well, it was created in 1998, 6. It probably went into mass deployment in 98, and it immediately started to get replacing by either PCI or PCI Express in the early 2000s. It was very short-lived. It did satisfy a purpose, but other technologies outgrew it, and system designers decided that it was time to put that technology aside and use other technologies. There was an extension made to PCI called PCIX. It was promoted by the Big Three in 1998. IBM, HP, and Compaq. Notice Dell wasn't there. Dell was not considered to be one of the Big Three in the 1990s. Even though they existed, they were a very small company. Again, it was short-lived. It was replaced by PCI Express. It made 64 bits wide, and it increased the clock rate to 133 megahertz. Here's an example of a PCI Express card and PCIX. In fact, I just did the same thing. Do not confuse PCIX with PCI Express. You're lucky you can't hear, because to my ear, I always have to ask somebody, did you mean PCIX or did you mean PCI Express? Because they sound very similar when they're spoken. Written, they're easy to separate. Spoken, they're very similar. But they're not similar when you look at the architectures. They're totally different architectures. So the answer to the question, will the bus ever end, is no. The current architecture,
I meant the PCI. Will that end when that PCI?
I believe that most of the motherboards you're going to see now PCI is gone. You'll start to read your motherboard, and we're going to talk about PCI Express. You'll start to see that your motherboard will have a whole, up to like 8 or 10 PCI Express cards. So they don't care anymore then. Because let's look at that, because you'll see that there's no reason now to have a PCI or a PCI X card. So in 2004, the group of 4, now the top 4 manufacturers, Intel, HP, Dell, and IBM, said, you know, PCI is getting really old. You can't really push it anymore. We need a new version. So they started from ground up. They totally changed the way the interface works. First thing they did is they got rid of it's no longer a parallel bus, meaning that the slots are now unique separated slots. If a card in one slot is operating, it does not interfere with a card in the slot next to it. So I don't have to ask for the bus to transfer data. It's a point-to-point connection. So I just send data to you and you send a response back to me. And on a separate lane, you would send the data. So in essence, it is pretty much like the express lane. The express lane on the highway runs independent of the rest of the lanes, and there's no multiplexing. In Los Angeles, you get a ticket if you actually try to move from the normal lane into the express lane, except at very small controlled intersections. PCI Express architecture wanted to do the same thing. It's as if somebody went down the highway and put a wall on each lane and separate out the lanes so that you couldn't move from one lane to lane. So you pick the lane you're in and you're stuck in that lane. You couldn't move. Now there's some positives and there's some negatives. The positive is there's usually a certain number of lanes that the chipset has built into it. It's usually a multiple of 8. It's usually 8 lanes, 16 lanes, and 32 lanes. And it's up to the motherboard manufacturer to decide how to carve those lanes up and how wide to make them. The specification says that there can be 1x slots, 4x slots, 8x slots, 16x slots, and 32x. So if I had a chipset that supported 32 lanes, I could in essence make one very fat lane. And that's all you get. It means you can only have one card taking over all the lanes. So like that house that's moving on the extra wide, you know, going up to Tahoe, you can't pass because somebody's moving the house and it's taking over the entire lane. Most likely what they will do is they will take the 32 bits and they will cut a 16-bit lane out for the video card. So if you read your manual, it'll say contains one 16x slot. That's usually for your video card because I need the fast transfer to do high-speed graphics. Then they might say that I have an 8x lane. And the 8x lane may be used for the disk controller because that's the second fastest thing that I have to have. You need to be able to transfer information off the disk very fast. And then they might chop the rest up into 1x slots. So let's go back and look at that motherboard. So this particular motherboard probably only has a 32x slot. Here's the 8x slot. Here's the 16x slot for the video card. There is no 8x slot in this design. Here's a 1x connector. Here's a 4x connector. And what you can't actually tell is that there's actually a transfer chip that takes most likely either 1 or 4x PCI Express and bridges over to give you the PCI bus. So it's a converter chip, but it has to occupy at least one of the PCI Express lanes to give you access to the PCI card. There are generally other things on the motherboard also that will take up lanes. So those extra lanes, I didn't add up to 32, right? I added all those up, I was not 32 lanes. There are other components on the motherboard, they're actually embedded PCI Express lanes that physically don't have connectors. Things like the network interface. The network interface needs a 1X lane. Technically, the network interface, you could get 2 of them for 1X lane. Because the speed of the original bus was 2.5 gigatransfers or gigabits per second. So I can support 2 1 gigabit Ethernet connectors in one PCI Express lane. And then somebody might make a 4 Ethernet connector card. But to do a 4 Ethernet card, I can do one of 2 things. I can implement it as a 1X slot, but then I have to say it's oversubscribed. Probably should have put that word in the dictionary. Oversubscribed means the amount of data coming in and the amount of data going out are not the same. So I lose some bits and everything. I might give you 4 slots, but you can't run all 4 at max speed. And you have to combine them into a slower speed. The other way I can implement it is to put the 4-port card onto a 4X slot. But when I do that, I end up losing or not being able to use the full capability of the bus. There's different lanes that I'm not capable of using because 4 times 2.5 gigabits is 10. Yes, 10. So it's not. I can never. The 4 Ethernet ports, I can never get 10 gig. For servers will use an 8X slot to support 2 10 gigabit Ethernet interfaces. So to support the newer standard Ethernet, I'll use an 8X slot because 8 times 2.5 is 20 gigabits per second. In 2007, they decided that they could speed up the bus and they allow 2.0 cards to now run 5 gigatransfers. They don't call them gigabits anymore. They call them gigatransfers. Full bus transfer per second. Because you don't know if it's a 32-bit or a 64-bit transfer, it's just transfer data. And then lastly, in 2010, the 3.0 standard has come out. You would just now start to see 3.0 cards available and 3.0 motherboards available, and you pay dearly for these. These are generally used for high-end workstations. Your low-end PC, the one you'll see in your Fry's advertisement for $299, getting ready for Christmas, most likely only have a 1.0 slot. It might have a 2.0 slot. Any questions?
Like games?
Games or CAD need high-speed video transfer. If I'm building a server, I might have lots of hard drives, so I need to have either multiple disk controllers or a disk controller that has a very fat data bus so I can transfer large amounts of data.
May I ask a question?
We have a question in the back.
So 3 years ago, I bought a system. I had it built for me at a computer shop. It had PCI, it had PCIe. The video card was something semi-fancy, but all that is gone now, it seems. And
So he's saying that he bought a machine a couple years ago. He most likely got 1X, most likely got 1X slots. Which, like I said, that's still probably okay. Those are still pretty fast. The video card was an 8X slot, so let's multiply that. It's 32, actually it's not counted. With PCI Express, you can't take the bus width anymore, because remember it says not a parallel bus. So it's actually a serial bus. So in this particular case, we have to take the number of lanes times the transfer rate.
So the lane would be
1X, 4X, 8X, 16X. Take the number of lanes that are combined together to form that particular slot. It's like this one here. This one's a 16X. Take the number of lanes, and then take the version, and that gives me the speed. So an 8X 1.0 card would be 8 times 2.5 gigabits per second. So that's 20 gigabits per second transfer rate from your video to your CPU. Most likely your CPU can't handle more than that. Anyways, some of the newer CPUs that have multiple CPUs on the chip, they can split that out and take advantage of the 2X and the 3X. So for that architecture, that's probably the limit of that whole system architecture can do. You're generally going to have a network card in a 1X slot. And depending on whether you like the audio that was on board, a lot of times people don't like the included audio card. And in some cases, they don't like the included video card. So if we go back and take a look at this particular example again. This particular example was designed to use chips that actually have the graphics processor on board. Again, when we talk about the CPUs, we're going to talk about this small class of Intel processors that actually have a graphics processor on board. So this particular motherboard is designed to take that chip and bring the graphics out to the connector on the back here. It's okay if you're not going to be doing anything fancy. So if you're building an email server, or you're building something that doesn't need a lot of graphics, and you just want to see messages, that's fine. Or if you decide not to use that particular chip, and you want to use a chip that doesn't have the onboard graphics, you really can't use this interface. So you will then put a graphics card separate in here, and the system will be smart enough, and it takes inventory, when the BIOS boots up, it takes inventory of all the hardware, and say, hey, I found a better graphics card than my onboard card. I'm going to turn off my onboard card, and I'm going to defer to this faster card. The same way that I was telling, was it Victor? What was it? Not Victor. Your name?
Yeah, Victor.
Victor.
Vince.
Vince, okay. I knew it wasn't Victor, but I knew it was him. Vince was asking on this particular motherboard, where were the hard drive connectors? The hard drive connectors are these multicolored ports here. You may not want to use these ports. We will talk about a system called RAID, R-A-I-D, which allows you to take multiple drives and combine them together to make one logical drive. And when I combine them together, I get a faster way of transferring data. So I might choose to say I'm not going to use these connectors, and I might, in that particular case, not put the graphics card in. I might put the RAID controller in the high-speed slot. Even though the RAID controller is only 8x wide, it can still go in a 16x slot. Can't go in a 4x slot because it's not wide enough. So here's an 8x slot, here's a 4x slot, but physically not the same. Physically can't put the card in the slot. But I can always put a smaller one in a bigger slot. So a lot of times this 1x slot here, a lot of times people won't even put this 1X slot on the motherboard. They'll just put the 4X slot in there, and they will let you jumper the motherboard to say how you want to use the slots. And so you can put a 1X card in a 4X slot no problem. I believe this ends tonight's official lesson.
One question. I have a special card.
Okay? Explain.
If I want to run TV on my computer, do I need a special card?
Depends on the motherboard. And these motherboards, yes, the answer is yes. Some of the motherboards will actually have an HDMI, high density media interface connector on the motherboard. Some of them you get there by converting the signal. Technically, I could get there using this motherboard. It's not easy to do, and I'll explain how you would do it. You can get an adapter that will convert the DVI. We're not doing video, we're just going to tell you how to do that. We'll go into details later. You're going to get an adapter that will convert the video signal from DVI into HDMI.
From
DVI, which is this white connector, into HDMI, which is, will come up later, which is that connector. This connector, though, which is used for VCRs, DVD, Blu-ray, cable boxes, is not just video. One second. It's video and audio.
UF plug?
UF?
RF?
RF plug.
Is that also RF?
No, these are RF style plugs, are also referred to as RCA plugs. There's no RCA out here. Technically, there's RCA for audio. So you could get a cable adapter and use the audio, which is usually signified by the white and red. So these three connectors here, white and red, signify left and right hearing, and yellow signifies video.
I don't care. I don't even use it.
Okay, so let me just finish my analogy. You might not care, but your daughters might find it very difficult when they come home and they want to watch a movie and they keep pushing the audio button and there's no sound. So in order for this motherboard,
That's how they get how I feel.
so in order to use this motherboard, I would have to find some way to take the audio, Jerry, from here. They'd have to find some way to take the audio from here and take the video from here and put them together to get into there, or they would take the video from this connector, go through a converter, go into there for video only, and you have to go on your TV and find the configuration that says audio is not on HDMI, and then you can take and make another converter cable to go from this connector to these connectors to get the audio. So the answer is yes, you can get there with this. It's not as straightforward as some new motherboards where there's actually an HDMI connector on the motherboard and there's an HDMI there. In the case of this laptop, there's a different standard. This one has what's called DisplayPort. It's signified by a D. You see a D? All right? No. A D with a P inside the D. It's similar to HDMI. It's not used for video. It's used for computer interfaces. But you can get a cable, much like I'm doing here, that converts DisplayPort directly into HDMI. With audio and video together, no extra cables needed. So you just have to look at your motherboard, look at your connector types, and figure out. And we'll get to all that. So you're like 6 lessons ahead of us. When we get to video and audio, we'll be talking about this.
Okay, good.
One of the things that we'll have to determine for this class is we will have to come up with a mechanism, a consistent mechanism for you to be able to test audio even though you can't hear audio. Because you might just be able to hold your hand to the speaker. That just tells you there's vibration. For me, who can actually hear, it could be screeching, it could be distorted, it could be a different language, it could be, you won't know. So we'll go through a couple things that you can use, some software that you can put on your PC or your laptop that will take in the audio, show you signal levels, and then if it's spoken word, you can run it through a speech to text to see if it's coming out in the right language. So you might have to determine, oh, this computer's speaking Spanish. Customer calls up, says, I don't understand my computer, it gives me all these messages, I don't recognize the language. You're going to walk in there and you can't tell because you can't hear. But if you run it into a program that can convert speech into text, and you can look at the text come across, you can say, hey, that looks like Spanish. Then you go onto the computer, you go into the language section, you find that they've set the computer for Russian or some other language. Okay. We have about 5 more minutes. I brought the other
Yes, a question.
Okay, I'll take your question.
I was wondering if the computer architecture was different for a Grantham computer.
For what kind?
The Q quantum computer.
Quantum.
Mm-hmm.
How old is the quantum computer?
No, he's talking about quantum physics.
Is that a manufacturer or a type of computer?
That's a different computer.
Type of computer?
Only exists in IBM research.
Quantum?
I think it means quantum.
Quantum, yes.
Yeah, so these are all general purpose computers that we're going to be talking about. I mean, they can be used in scientific, they can be used in business, they can be used for gaming. There are different types of processors and different types of computer architectures that are designed to solve very specific problems. And in some cases, they use common components. They might use general purpose components, but the way they put them together forms a specific design. IBM has a computer that used to be the fastest one in the world, Deep Thought or Big Think or something. It was made up of many different Pentium chips, all interfaced together. Each individual board was much like a PC. And when they were interconnected and formed this giant arrangement,
But quantum, it doesn't use, it's a different processor, it doesn't use
I
zero
was
one.
about to answer this question. So, by putting all these processors together, it forms a logical array processor. So there's a concept of an array computer, array processor, where each one is a cell, a very large square matrix, and the processing in parallel massive amounts of data. Each cell is responsible for a very small portion. And for a quantum computer, I've heard of it, I'm not sure how the architecture actually works, but these array computers are used for like oil drilling simulation. What happens if I drill here? What will happen to the water table? What happens to the ground? And then if the ground changes, what happens to the water table? So they go through all these parallel analysis of what the outcome might be for drilling here to try to figure out what the highest probability is. Earthquake analysis. You know, when an earthquake hits and they try to understand if this is going to cause more earthquakes, they run scenarios with these big array computers to say, this event occurred, is it going to trigger this event, is it going to trigger that event, is it going to cause this to slide? If the ground slides, is that going to cause an earthquake in Los Angeles? They run all these simulations really quick, but they need to run it in an array because they're trying to do all these things at the same time. So they can quickly call up LA and say, hey, issue a warning because you might have an earthquake tomorrow. Or call up the drilling guy and say, hey, stop, don't drill there because that drilling might cause the water in the lake to spill over into the river and some other. So for quantum, they're really looking at molecules and how the interaction of the electrons. It's a very similar problem because they have to model something they physically can't see. And at that level, there's a thing called Heisenberg principle where Heisenberg principle where you know where the position of the electron is, or you know how fast it's moving, but you don't know both, and by trying to observe it, you change it. So they can't actually gather the data by looking at it. They have to gather the data by simulating it. And when you got a million molecules, the problem gets to be really big. And again, they have to use a very large, wide array computer to look at all the interactions that occur. Even trying to collect data from like the collider takes a very large computer. There's so much data that came at the same time. It's a big computer problem to try to analyze. Even the stock market analysis, because I might buy a stock which Jerry sells, which Chris buys, which then causes Vince to sell, and then all of a sudden the whole market crashes. So they look at all the scenarios, and what they want to do is they want to get ahead. They want to know before Jerry sells, I'm going to sell, so I get a better price than Jerry. And then they want to get in and they want to buy before Chris buys, because they want to get a better price. So they're looking at the trends to jump ahead of the human to make the purchase or the sale. And they have to do all this analysis because Microsoft stock is affected by IBM stock, it is affected by Apple stock, which could be affected by the price of wheat, which could be affected by the price of gasoline, which then is affected by the transfer rate between the U.S. So all these different interactions occurring, they have to be calculated many, many times and in parallel. And they take very, very large computers.
I see. How about that DNA, that dialysis? Where's that? Yeah.
You have to do a lot of similar things because you have to, one of the things about DNA is you have to separate science fact from science fiction. In science fact, when they get done, they don't end up with very long, they end up with these little fragments. And they're expecting to get lots of little fragments and trying to line them up in sideways to try to figure out what the actual fragment, what the actual length actually looked like. They never get a full intact piece of the DNA. So it's like a puzzle. I won't know what the picture looks like until we get all pieces lined up. So they'll try to line these pieces up to try to make, and it takes a lot of calculation. A lot of computers constantly shuffling the pieces around. As if you made a computer program to solve a jigsaw puzzle. Think about it over the weekend or before Thursday. In your own mind, what would you have to tell the computer? What kinds of things would you have to tell the computer about how it would solve a jigsaw puzzle? It's going to look at colors. It's going to look at shapes. It's going to look at the fact that this is an edge piece versus a center piece. It's going to look at the fact that if I use this piece here, I can't use it there. So if this is the lower right corner, it can't be the upper left corner. So there's all these rules that you have to tell the computer program. And they have to do the same thing with DNA. DNA extraction and analysis is still, I personally wouldn't trust it. I don't think it's infallible. I think they make a lot of mistakes. Because they get a jigsaw puzzle. They don't get a picture. They don't get a photograph. You get a box with 1,000 pieces. We have a saying, by the way, related to that. GIGO. G-I-G-O. in essence, it means the computer is only as good.
Garbage in, garbage out.
Garbage in, garbage out. The computer is only as good as the information you put into it. You can't just walk up to a computer and say, you know, who should I marry? How's it going to know the answer to that? It's based on
No
what
emotional thinking.
it has no logic, you know, like Spock, you know, it can't calculate anything other than what you tell it to calculate. Yes, we used to, in college, we drew this magical piece of computer gear. It was called the XB2000 Mind Reader. Because too many times, in those days, we had to punch the cards. Remember we talked about the cards? We had to punch the cards, and we'd constantly be making mistakes. So this magic device would do what you wanted to do, not what you told it to do. I don't care what my card says. That's not what I wanted you to do. I wanted you to do this. So it would read your mind and say, okay, I'll ignore your cards, and I'll do what you really wanted to do. So you would need one of those. That doesn't exist. There's no way they can make one. Science fiction may be saying they could do it, there's just no way to get there.
But they have a machine that reads dreams, but it's not
No.
good, but.
No, it can't read dreams. It can read impulses. Some human has arbitrarily decided that this impulse means this thing. It was his decision, not a computer's decision. And how do you know that that guy's theory is 100%? Things like neuroscience and on DNA and subatomic physics, every 10 years, a new theory comes out. And they take all the paper, they tear it out, and they start over.
Okay, our interpreter's tired.
Yes,
And
I'm
we're
understanding, we're out of time.
we're running out of time, so
Right. We're done.
we're torturing him beyond the amount that he's contracted.